Alright, welcome back to another video. My name is Professor Collins. Today we will be reviewing Chapter 5. The basis of understanding Chapter 5 is understanding chemical energy. So similar to potential energy in like physics that you've learned before, but it's within chemicals.
Wait, I have a question.
You have a question? Okay.
I'm only in 121 right now. 120 physics, sorry. I'm only in physics 120 right now. Am I prepared for this, would you say?
Definitely.
Okay.
Yep. Not too much math involved.
Gotcha.
Yeah, but you have to be prepared.
Well, I enjoy math.
It's great. Love to hear that. Need that energy here. All right, yeah. Good way to think about it. Think about a car burning like gasoline. You know, that is releasing energy, which is going to power your car.
It's not good for the environment, though, Professor.
Unfortunately, yeah, it's not good for the environment. Yeah.
Go on. Sorry I interrupted.
So, the basic law of thermodynamics states that energy cannot be created or destroyed. So, whenever we're analyzing a system, we have to take into account that energy is either coming or going somewhere else. All right? And this especially goes for solids, liquids, and gases. Solids have the least amount of energy. Gases have the most. Gases have a lot of energy. There are two different types. There are endothermic and exothermic. Write those down. Endothermic. Endothermic is when energy is absorbed by a chemical. All right. So it is in the
product.
An endothermic reaction, the chemical needs energy in order to, it needs to be given energy in order for a reaction to take place. Second, exothermic. Exothermic is the opposite. In an exothermic reaction, chemicals release energy. Energy is part of the product.
Reactant.
In the end.
What's up, Professor? My way to think about it is X out. Rolling.
All right, when analyzing a system's change in energy, we want to analyze it as such. What are Q and W, you're probably wondering. Well, Q is the heat. And W is the work applied on the system, which you definitely have heard in physics before. And so to find if it's positive or negative, you have to see with heat, you have to see if it's being entered into the chemical or if it's leaving. If it's losing heat, it's negative. If it's gaining heat, it's positive. With work, if a work is applied to a chemical, then it is it's positive. But if the chemical is applying a work, then it is negative. The main piece of this chapter you will remember for the rest of your working lives.
No way.
Enthalpy.
Professor, what about gravity?
Ignore it. What? This is everything. It's everything right here. Enthalpy is the change in heat in our class. In reality, we have to take into account pressure and volume, but here it is always constant. So enthalpy is simply change in heat. Look at that.
Wasn't there some sort of song?
Delta Q.
That.
Enthalpy. Enthalpy is the change in heat.
Oh, change in heat.
Yeah.
P is momentum.
You got it.
Oh, P equals MP.
Professor.
Yep.
P. Oh, okay.
P equals MV.
Yeah. All right, and then so we can only measure changes in enthalpy. Enthalpy is internal energy. We can only measure the change. We cannot actually measure what it is internal energy of a chemical is at a certain time. All right, here's our first practice problem. I'm going to have somebody from the class calculate the change in internal energy in a system that absorbs 200 joules of heat and applies 100 joules of work on the surroundings. Clyde, come to the board. Do the problem. Okay. Not quite. Klein was correct in having 200 joules of energy being positive because it is being absorbed by the system. However, with the work, 100 joules is being applied by the chemical on the surroundings. So this right here would have to actually be negative. And then this right here would be 100 joules of energy. All right. Horizontal.
Rolling.
All right. Next up, we got specific heat, and the abbreviation for this is CS. You'll see this a lot. And this is the heat required to raise 1 gram of the substance by 1 degree Celsius. The unit for this is going to be joules grams times degrees of Celsius. Now it's really important to remember that this is in joules and not kilojoules, because a lot of problems will be in kilojoules and have to be converted to joules because the specific heat given will be in joules per grams Celsius.
How do you convert to Kelvin from Celsius?
There's no need to do that for these because
Okay.
it is simply the change, and the difference between Celsius and Kelvin is the same, but it's just it's at a different level.
Okay.
Yep. And so this leads us to the equation Q equals M times the mass times the specific heat times the change in temperature. This is essential. This is the essential equation right here to finding heat. Good. Applying what we've learned so far, we get to calorimetry and reaction enthalpy. Reaction is abbreviated RXN in many places here. All right, first question you gotta ask yourself when you see a problem like this is a reaction involved? Is a chemical reaction occurring? If no, it's probably just a thermal equilibrium problem, which is real simple. You're gonna be given a system, which is any object, like a metal sometimes it tends to be, and the surroundings are almost always gonna be water. And you're gonna be given various heats. You're gonna be given variables that are all within MCAT, and you're gonna be asked to find one variable in this system. Those aren't too bad. Where it gets a little difficult is in these reaction enthalpy problems. So your system is gonna be a chemical, and this could be anything. This can get real complicated. And the surroundings, it varies, but it usually tends to just be the universe, so it's just being let out or being taken in from like an unknown source in a sense, or sometimes it's water. And you must find right here the enthalpy reaction, which is the heat that is released per mole. And we're gonna do an example problem to show you what that looks like. All right, so here we got our example problem. We have this substance right here, NH4NO3, that dissolves in water. It lowers the temperature. And we have 4.25 grams of said substance in 60 grams of water. And in this reaction, the change in the temperature of the water is negative 5.1 degrees Celsius. So water getting colder, clearly it is an endothermic reaction because the chemical is absorbing that heat and taking it away from the surroundings, which in this case is the water. And here's our balanced chemical equation. Thankfully, we have all ones at the start, which makes this a whole lot easier. So first thing we're gonna do is go with the overall system's change in heat. And we're gonna use our trusty equation up here, MCAT. And we're gonna do 60 plus 4.25. It's important to remember to add the mass of the chemical. And multiply this by the specific heat of water, which is always given, 4.186. And then we're gonna multiply this by our change in temperature. So this is for the water. Negative 5.1. And so this yields approximately negative 1370 joules. That's our number so far. And so our final is always going to be in kilojoules per mole. So we're going to convert this to kilojoules, which simply divide by 1,000. And we get negative 1.37 kilojoules. It should be 2 sig figs clearly because of the 5.1, but we're adding 1 just for better calculations. Now for this, we need this Q value, which we just have right here, over moles. First things first, we're going to flip the sign because this is for water, and the inverse, because of Q surroundings plus Q system equals 0, the inverse is just going to be simply plus that, so we can, that is the change in heat for the chemical. And for moles, we want to find, we're going to divide our grams given by the molar mass. So what we're going to have here, 1.37 over 4.25 divided by the molar mass of our substance, which is 80.044. And with sig figs and everything, this eventually comes out to 26 kilojoules per mole of NH4NO3. That's our final answer. Good. So enthalpies of formation. Finding the actual enthalpy of formation is not really done in this class. We usually just consult the back of the textbook, but you will need to know how to write the equations, formation equation. The best way of showing it is simply an example. We have NaNO3 here, and as you can see, Na, there's one of them, it's just simply Na. Now, consulting Brinkelhoff, we get to the diatomics, and that's when it gets a little interesting because we have to express this as N2. And then, we haven't been able to do this before, but we can actually use a fraction here. So 1/2 times 2 is equal to 1, expressing the 1 nitrogen we have in this substance. Same thing goes for oxygen. We have 3, so we must divide this by 2, and then put a 2 in oxygen. So we get 3 over 2, O2, which gets to 3. And it's also important to know the states of matter. As you can see, this is a metal, and metals are always going to be solid at room temperature. So these are all, you got to put the state of matter that's at 25 degrees Celsius. And nitrogen and oxygen are always gases. And you have to just, before the test, go to the periodic table and look up which ones are which. And it generally follows that non-metals are gases, and metals are solids, and then mercury and bromine are liquids, and there's a couple other exceptions. But look over that before the exam, and you should be good to go. All right, so Hess law is going to be the sum of the enthalpy change for each step. And so we're given various equations that are steps in making this final equation. And we want to be able to order them in the proper way to get the final answer. The best way of showing this is simply do an example, because this is what the problem you're going to see on the exam looks like. So what you want to do is you're going to get a different color pen, and you're going to locate the ones that are in the final product. So you got CS, oh boy, whatever. You got CS down here, and now we got H2O, and it's H2O is down here. CO, we got CO over here. And H2, we got H2 over here. So left over, we got CO2 and O2, which are like most likely just going to cancel out. We'll worry about that at the end, but most likely they will cancel out. What we got to worry about is ordering CO, CS, H2, and H2, and CO in the proper order so they can form a final equation that is this. And then we have to count the steps of enthalpy. We have to do the same manipulations to these as we do to these, and that can give us a final enthalpy value. So CS is in the reactants, and it's got a 1 in front, same right here. So this is just simply going to stay the same in our final calculation. Negative 393.5. 2CO, on the other hand, it is 2 here compared to a 1 here, and it's on the opposite side. In order to switch sides, you have to multiply it by a negative. And since it goes from 2 to 1, we have to multiply it by half. So we multiply this by negative 1/2. So plus negative 1/2 times -566. Now for this one, we have two values. We see H2 and H2O, which both of them are in the wrong side and both have 2's instead of 1's. So it's just same as the last one. We're going to multiply by -1/2. And doing that, we take this value, we add it multiplied by -1/2. And this all comes out to equal 131 kilojoules. That's our final answer. All right, we're good.